Hello everyone, I'm Eris. Today I'm going to talk about progressive simulation for class Quasistatics, and this is joint work with my collaborators Jérémie, Raymond, Alec, Doug, and Danny. So interactive design of high-quantity class simulation in 3D modeling softwares should be as simple as laying out class in the real world. However, in fact, this still remains as a challenge, and let's take a look at why. On the one hand, high-speed methods for class simulation are now reaching interactive rates for extreme-scale class meshes. But because of the simplifying and limiting assumptions made in the simulation model, its expressiveness is largely restricted. Even worse, in some context-rich scenarios, the simulator can be incredibly unstable and sometimes generates undesired creasing and intersection artifacts too. On the other hand, high-fidelity methods like IPC are growing increasingly expressive, with simulation results that closely mimic and even in some cases accurately depict the world around us, but in general, they are still far away from reaching the interactive rate. But is it really impossible to get the best of both worlds? Here, we want to get the beautiful and realistic faults, wrinkles, and contexts that those high-fidelity methods provide with us, while still giving interactivity to the users. And most immediately, we are looking at how to enable interactive exploration of class design parameters. And essentially, here we are inspired by the success of progressive refinement strategies in rendering and geometry from both these old works and some recent advances these days. It sounds like a natural fit to class simulation because wrinkles and faults could similarly have different levels of details. But the question we are facing is how we can actually extend progressive methods to class simulation. Well, to enable progressive simulation, there are a number of challenges that we will have to overcome. So one obvious approach is to design a scene using a very coarse-res interactive simulation. And then, once all material and layout parameters are finalized, finish up the simulation with a finer resolution mesh. But this immediately runs into trouble. You could say part of the fine sheet got stuck at the armadillo's nose, and moreover, low-res and high-res wrinkle patterns do not match with each other. Alternately, we can try cascading the simulation, that is, warm starting each finer simulation solve from the last one. But this also doesn't work because mesh-based class simulation suffers from the known membrane locking issue if using a too coarse geometry, and the fine level simulation will exhibit those sharp creases and kinks all the way up. Lastly, although linear multigrid similarly maintains a hierarchical structure, we can't just apply linear multigrid to solve our overall progressive problem. The main reason is the ultimate goal of multigrid as an iterative solver is to make the finest level linear solve faster. But the coarser level in between solutions are neither meaningful to visualize nor ensuring any consistency. So it's orthogonal or say complementary to our goal, and designing a multigrid solver to accelerate IPC is then interesting future work. So to achieve both high quality and interactive simulation, we propose progressive class simulation, PCS, a new forward simulation method for efficient preview of class quasistatics on exceedingly coarse geometries with consistent progression across resolutions, produces reliable, stable, and intersection-free simulation, and also supports interoperability at any point for parameter changes, and also interactive preview with consistent coarse-level simulation. So consistency gives us corresponding previews across levels as we refine, while convergence gives us controllability and expressive range, say changes in known real-world parameters. And for example, the materials we used here, it gives us corresponding expected changes in the simulated shapes. Meanwhile, PCS not only produces artifact-free coarse-level preview simulation, but at the finest level of refinement, also gets the same converged and so high quality result as if we directly use the IPC method at fine resolution. As a bonus feature, PCS achieves an order of magnitude speedup compared to direct simulation at the fine level, assuming we know the entire parameter settings at the beginning. Because of all these features, PCS enables users to interactively and progressively explore class design parameters, so we also build up an interactive tool around it. Here's an initial setup, where the user manipulates class, colliders, and materials, and later produces a low-res draping. During pauses, our solver automatically improves to consistent higher-res drapes, while user iterates on the low-res mesh for more interactive editing. When the user is satisfied with their design, refines offline to final highest res geometry. Here is a prototype of our tool and a few different types of interaction that it supports. So first of all, you could say the mesh geometry rapidly refines when there is no user interaction. For collision resolution, it gives asynchronous responses, so the class will gradually catch up as the collider moves around. And following that, users could also plug in real-world material parameters and change them on the fly. For object manipulation, users could translate, rotate, and scale the collision geometries, or even attach some handles to manipulate the class. When all is starting to look good, do some local fine-tuning. And in the end, after a few more progressive refinement steps, you could sense this converged fine-level geometry to some production-level renderer and get these beautiful final drapes full of fine wrinkles and details. So how does PCS actually achieve this? Before we jump into the method, let's remind ourselves with some high-level goals. So given some initial condition, say this class over bunny example, we always aim for obtaining high-quality, fine-level simulation results. But before that, we also want a predictive and efficient coarse-level preview simulation, and meanwhile, progressive and consistent improvement across levels. Regarding how we get from the initial state to the final converged shape, like many other physics-based simulation methods, our objective at the finest level is always this incremental potential problem, which is a variational form of the discretized equilibrium equation. And notice that we don't care about the dynamics in between. Specifically, the objective energy E could be further broken into two parts, the elastic and contact-related potentials. Here, psi and phi are membrane and bending energies, while B is contact barrier, D is the friction dissipation potential, and S is the strain limiting barrier. We encourage you to read the original IPC and C-IPC papers for their detailed definitions. And after some optimization steps, the state will converge to a local minimum of the energy, where each local minimum corresponds to an equilibrium state, which is exactly the thing that we are looking for. Since we are facing this multi-resolution problem, for each piece of the deformable class, we also maintain a mesh hierarchy from level 0 to level L, with increasing resolution, where the number of levels to use is up to the user's choice. Inspired by multigrid methods, depending on the way the hierarchy is constructed, we could also construct a corresponding prolongation operator to transform information between different levels, and we use modified loop subdivision, which preserves boundary as a default choice. And please read our paper for discussions of different alternatives. Following that, for each level, a corresponding incremental potential problem could be constructed based on the mesh discretization. And similarly, each local minimum of this energy EL corresponds to a converged shape at this level. And when it comes to how we actually optimize this energy, instead of directly going from x0 to x star, we break this process into a sequence of sub-steps and apply this so-called artificial time-stepping strategy based on implicit Euler. To notice, the core idea here is to add an inertia term to promote continuity across quasi-static time steps and stability of the linear system to solve, while ensuring the original objective energy is always decreasing by construction. However, if you simply optimize these per level energies, say E0, E1 to EL independently, you will see these creasing artifacts due to coarse-level membrane locking issue as I mentioned earlier. So how could we do better and smarter? So instead of being blind to finer levels, we want coarse-level to have fine-level information. And motivated by this, we construct this coarse-level proxy energy, FL. Notice that here we are also taking advantage of the prolongation operator as I mentioned earlier, and PL can be pre-computed and directly prolong information from the current level to the finest level. Similar to the original incremental potential, we again could break FL into two parts. The barrier part for handling contact constraints, etc. is identical as before. However, for the elastic part, we use the finest level energies by parameterizing it with the coarse level degrees of freedoms using PL, or in other words, we prolong the coarse level state to the finest level and evaluating the elastic energies there. The intuition is to sample the actual fine level elastic energies but use the coarse level geometry to handle contact. With the level increasing, you may notice that this proxy energy is getting closer and closer to the true fine level energy. Again, as for the actual optimization strategy, we could similarly use the artificial time-stepping way. And together with it, apply a Newton-type descent optimizer like in the original IPC paper for contact handling. And one thing worth to mention here is when running these Newton steps, we fit a sequence of quadratic functions as approximations and hence solve a linear system which requires to compute both a gradient and Hessian of the proxy energy. And if you further expand the expression of the Hessian part using chain rule, you may notice that although the left-hand side matrix has the same size as the original coarse-level system, to deal with the middle term, the cost is similar to evaluate original fine-level Hessian matrix. So to further reduce the computational cost, we simply replace it with original coarse-level Hessian. After some steps, it also converges to a local minimum under user-specified tolerance, and for details of the convergence behavior, please refer to our supplemental. Alright, so far we have both a well-defined proxy energy and an optimization strategy to minimize it. But we are still missing one important refinement step, which is to go from the current level to the next finer level and obtain a feasible initial state there. However, if you naively apply the prolongation operator to appraise the coarse geometry, it could potentially cause intersections and violating strain limiting constraints. To remedy this, we propose this safe prolongation step for contacts, and given that we already know the coarse-level converged shape is intersection-free, we first apply the prolongation operator to obtain a target shape, and after that, do an in-plane upsampling operation by inserting new vertices on the edge to get a safe initial state. This is to make sure the upsample geometry has the same topology as the target shape while not violating the contact constraint. And lastly, we run a continuous collision detection step to search from the safe initial shape to the target shape, which returns the largest step alpha. Combining all these pieces together, we'll get a safe initial state for level L+1. Well, but contact is only half of the safe prolongation problem. That is to say, although the safe initial shape we just obtained is contact-free, it could still potentially violate the strain limiting constraints. And to be more specific, the principal stretches of each individual triangle are over some limits. To also preserve SL constraints during prolongation, we construct an efficient nonlinear optimization to safely refine while not violating existing contact constraints, essentially by maintaining a dynamic set of infeasible triangles and adding an ARAP term to pull each triangle's principal stretches below their limits. Due to time limit, I won't go into details here, but please see our paper. So having all these different pieces together, we finally have a complete PCS pipeline which consists of both the coarse preview and the progressive refinement stages. It's also worth to mention that this refinement process is never a one-way trip. Whenever there is any user interaction and material update, the solver will just go back to the coarse level and recompute, which is an important thing for the creative workflow enabled by PCS. Now let's take a look at a few more results and demos. So first of all, we compare to some existing implementation of those fast methods like Houdini Vellum and Marvelous Designer. And you could say numerous undesirable creasing artifacts at low mesh resolution. And after trying to appress coarse class designs by then rerunning them at high resolution, leads to weird material stretching in Vellum and explosive instability in MD. However, those artifacts are notably absent in the coarse-level PCS simulation, and the finer levels always give high-fidelity and artifacts-free solutions. Meanwhile, we also again compare to the Cascadic approach in the sensitive couture paper. Beyond just the Cascadic artifacts, there are also this inconsistency issue where the wrinkle patterns do not match after passing through a few levels. In contrast, PCS provides multi-level consistency so that the original coarse-scale faults progressively refine predictably. And this is another example for which we change the base mesh triangulation, and PCS always does a good job on resolving the membrane locking issue while maintaining consistency. For consistency measure, so far these are just vero comparisons. Another quantitative measure is look at the change in wrinkling, and one way to look at these changes is principal curvature. Here I'm showing in red the major points of principal curvature and normalized per level to give a sense of the significant faults. You could say the overall pattern is generally the same, but with finer and finer details with resolution increasing. And how about quantitative measure? In our paper, we take the first step towards a quantitative measure of wrinkle consistency by integrating the area-weighted mean curvature difference, HC minus HF here, over the whole mesh domain omega between corresponding coarse and fine levels and get a scalar value dH. And in this figure, we compare the point-wise difference in the mean curvature for the previous inconsistent example of SC and PCS on their common flat-based domain. And here you can see the SC method exhibits regions of large difference in curvature. And since inconsistency is a major issue with direct simulation, we also run a benchmark to compare with PCS and shows PCS wins by orders of magnitude through comparing this DH value across all the examples. Please see our paper for more details. Moreover, beyond using the same mesh for collision geometry at all levels, we could similarly replace it with a nested hierarchy to further reduce computational costs at coarser levels while ensuring contact safety when moving to the next finer level. And our experiment shows that PCS could still produce consistent results in this case. And also in this material gallery, we vary bending stiffness and plug in real-world material parameters to get a variety of realistic wrinkling behaviors. Having all this together, we also showcase a creative workflow enabled by PCS and our interactive tool. In this rainbow twisting example, we could say PCS enables handle-based class manipulation with contact to interactively twist class against itself, rapidly forming complex, tightly wound geometries from simple input shapes. And in this still life example, the user is trying to set up a table class. With PCS's robust collision processing, users can also directly apply transforms to complex collision objects to intuitively push class around and between ships. As equilibrium is reached for edits, PCS automatically starts progressive simulation to finer level solutions. And when no further edits are desired, the user could just go to grab a coffee, and after a few minutes later, come back for a converged, high-quality, non-intersecting result for tightly nested and complex geometries. For future work, one immediate next step is to further improve PCS consistency. For example, to better handle some challenging configurations like highly twisted and crumbled claws. More broadly, we could consider extending PCS framework to support shells and volumetric solids, and also dynamic simulation. Finally, our progressive simulation is a natural fit for dataset generation in supervised learning of class simulation upsampling. And in the end, I thank all my co-authors again for making this work happen, and thank you for your attention.